So I had created a post about coroutines, and I made an example called SumTask, which added two numbers. And so this is a very simple coroutine, and I decided to create a more classic coroutine example, and I created this namespace called TimerTask. And what TimerTask does is it creates timers, which after their time is elapsed, they execute some sort of code. And all of these timers are coroutines. So they all execute in one thread as coroutines, all of these timers that are executing disjointed code segments. So this process basically it includes declaring this timers object. And this object is going to use a background thread to run some group of timers. And so an example of adding a timer, this is the code that's going to print when the timer executes. It's going to execute in 10 seconds, after 10 seconds, or every 10 seconds, and whether it should continue. And so this has a should repeat and repeat count. So when we run this program, we get the timers printing. There's one more timer, the 10 timer. And this one will keep printing every 10 seconds indefinitely. So this coroutine consists of, it's called task, and the coroutine is task as well. So this timers object basically in add, it goes to add the task. This is a task added in the group method, and a task consists of the timeout number, the function, whether to continue, and if it repeats, and how many times it repeats. And so it's going to take all of those coroutine instances. Normally in C++, when you create an object, there's like a constructor that you use. But in this case, this task is a function, and it's returning a coroutine. So this task function is the coroutine, and that's apparent because it calls co-yield, and it returns a task, which is a coroutine, which I'm going to talk about in a minute. But so when the task is first created, it has all the parameters: timeout, functor, repeat count, and then it is suspended. All these timers, when they're first created, here, they're suspended. And then once a timer has been added, it calls this method run in a separate thread, a background thread, which is referenced with timers future. This run method first, it copies all the timers that have been added into an active timer list, which is mtasks. And then for each task, it calls resume, which is a coroutine function to run this task. So resume calls, it will return to where the co-yield left off. In the case where we haven't called task yet, it starts at the beginning like a normal function, goes to co-yield, and then it returns. And so all of those tasks are ran in sequence. So there are a bunch of these tasks that are ran in sequence, and each task handles the timer logic on whether to call functor and whether it's expired. And so this co-yield method, it yields values, and these values are, we want to communicate to the caller, potentially. These are values that are going to be exported to the caller, and we do that with the yield. And so there's this method, done, and it returns if the timer future is still running timers, because after a timer runs, after the timer logic runs and co-yield is called, it will erase any timers that are expired from the list. And then it'll keep running all of this for as long as the list is not empty, which means so this expired is accessing the co-yield data. T.expired is accessing this co-yield expired right here, and it does that through the coroutine interface. And the coroutine interface is task. Task has a thing called yield type. Yield type has a count, which is the amount of times the timer has executed, and it has expired, which is whether the timer should be deleted. And so a coroutine has this type called a promise type. And from there are these objects, standard methods. Specifically, the yield type is inside the promise type. And so when we call yield value, yield in the coroutine, it calls yield value here, and it passes in the yield type, and it gets saved. So this here, when we want the coroutine to return, it saves these two values into the current value and returns suspend. So then it returns to the resume. And then in the caller code, expired accesses, is this function expired, and returns the promise type expired value. So this is accessing the promise here. And so this task for the coroutine is used to pass the yield type around from inside the coroutine to outside the coroutine via current value. These are the methods that expose the promise to the caller. And so once it is expired, it will yield and save this data, and then expired is accessed here, and it is then removed from the task list, and then yield. So if all the coroutines are relatively quick and there's not many of them, then most of the time will just spent be yielding. And as long as there are tasks and we have not called stop, then it's going to continue to do this indefinitely. And so the timer's destructor calls stop. Stop will wait on the time future if it's not already complete. So this is kind of neat because I think this is like the kind of classic coroutines example, is having timers. And so in these timers, you can affect a system. Say you have some system. You could add a timer. And call a so these timers can call into your system or pass messages. Anyways, this is available on my GitHub, and I'm not sure what I'm going to be doing with this, if anything. I don't know. I think normally if you wanted to use timers, you would use this thing called ASIO, which is available through Boost. And I think they also use coroutines possibly. But this specifically is created to be an overview of how to write these coroutines and encapsulate them, and it seems to have been pretty successful.